Hey everyone, I am Mana, and in this tutorial I want to show you what Weak-Heap is, how it can be created, and how it can be sorted. Weak heaps are a variant of heap. Specifically, they are similar to binary heaps and binomial heaps, sharing several features. For example, it has the efficiency guarantees of binomial heaps and can be sorted in an array as an implicit binary tree like a binary heap. I will explain the differences of binary heaps and binomial heaps in details after indicating weak heap properties. The first property of weak heaps is that every key in the right subtree of a node is smaller than the key stored in the node itself. For example, look at the node 2. Its right subtree is its right subtree is 1 that is smaller than 2. And this condition is applied to all of the nodes. And finally, we have the root with key 17 that is greater than all its nodes which are in its right subtree. The next property is that the root has no left child. And the third one is that nodes with less than 2 children are in last 2 levels of the tree. Now we want to see the differences between binary heap and weak heap. As we mentioned before, the root of weak heap has no left subtree. The second one is that leaf nodes of weak heaps are not required to be as left as possible. For example, here you can see that we can add a key node of 5. And finally, there is no relationship between a node's key and the key in the left subtree, of that node. For example, here, the left subtree of the key node of 13 has 2 nodes greater than 13 that are 15 and 14. Now we want to see what is merge operation. One of the most important operations in weak heaps is that how we can merge two heaps. So consider we want to merge these two weak heaps. First, we pick the greater root, which is 17 here. And then the other root with its children become the right subtree of the greater node. Finally, the left children of the greater node becomes the right children of the smaller node. Now we have a new weak heap that satisfies all the features of weak heaps. Now it's time for array implementation. To implement the merge procedure described in previous slides, 2 arrays are used. The first one is the element array H by using breadth first search, and the other is the reverse array of reverse beds. As you can see, we can find the index of each node's right and left child and parent by the presented formulas. Also, the reason we make nodes 3 and 7 gray is that the reverse bits are set to 1. Why is the reverse bit set to 1? Because node 3 with its children must be a weak heap. So when we swap the nodes 6 and 7, it will become a weak heap because the key node 2 is greater than the key node 1. Now we want to sort this weak heap. For sorting a weak heap, we remove the root and put it into an array H1. Then from right to left. Then make a forest of weak heaps of these nodes. After that, we merge the 2 smaller weak heaps as we mentioned in previous slides, and finally we have a new weak heap. And we repeat this procedure and remove all the nodes and put it into the array. Now we remove 15. Then we remove the key node 13. And after that, we remove the key node 10 and put it into the array. And now we remove the last node, two last node, which is 8 and 2. And now we have a sorted list of our weak heap. About the analysis and empirical results, the resulting sorting algorithm has a number of comparison less than n-1 log n plus 0.086 n, while the original heap has the worst case of 2 log n. Also, heap sort variants such as bottom-up heap sort and MDR heap sort have the worst case of 1.5 n log n minus 0.4 n and n plus 1 log n plus 1.086 n respectively. As a result, Weak-Heap Sort needs fewer compares to other heaps, making it a good sorting method. I'm very thankful you watched this video and I hope you have a great day.